Today we're going to try to complete our discussion of quantum error correction. In my view, along with Shor's algorithm, quantum error correction is one of the two great accomplishments of, up to now, of quantum computing. We mentioned in the last lecture that it's absolutely essential to be able to do error correction for quantum computing, in particular because the devices which encode the qubits are very small, often only atomic size, so they're easily perturbed. And furthermore, errors can grow continuously out of the original states, which is not the case for classical computing, where it's 0 or it's 1, there's nothing in between, but in quantum computing there's everything in between. We pointed out that in order to do the error correction, we're going to need to do some sort of duplication just for classical error correction. We're going to assume that the error rate is small, so at most one bit will have an error. And we're going to restrict ourselves initially for simplicity to illustrate the concepts with a simple case where we only assume there can be bit flip errors. Okay, we'll come to that. You're right, thank you. Where was I? Okay. So we connect the state which we want, which will in general be some linear superposition, to some ancillary qubit, and then we're doing the measurements on the ancillary qubit. We can't do the measurement to see if there's an error on the state itself, because that would destroy this linear superposition. So what I was saying was that in addition to bit flip errors, in the quantum case, there are also phase errors, and you can have combined bit flip and phase errors. In the first example, we're just going to try to error correct bit flip errors. Right. So this is incorrect, as was pointed out to me. No. So we will, by analogy with what was done classically, the state 0 will be encoded in 3 qubits, 0, 0, 0, and the state 1 will be encoded in 3 qubits, 1, 1, 1, and we're going to see if any of them are flipped. So we have to be able to cope with a linear combination of 0, 0, 0 plus 1, 1, 1, with the possibility then that any one at most of these 3 qubits might suffer a bit flip, a random flip. So maybe this gets flipped, maybe this gets flipped, maybe this gets flipped, maybe none of them get flipped. So we couple these 3 physical qubits of interest to these 2 ancillary qubits with these control not, or equivalently control X gates. So the 4 states that we have to distinguish, which go under the name of syndromes, that includes the uncorrupted state and the possible corrupted states that we're going to be dealing with. Collectively, they're called syndromes. So psi naught then is the uncorrupted. Psi 1 has bit 1 corrupted, and I'm going to put the rightmost bit will be bit 1. Psi 2 has bit 2 corrupted, and psi 3 has bit 3 corrupted. So you can also think of psi 1 is obtained by acting with the X operator, the bit flip operator for bit 1 on the uncorrupted state. Psi 2 is you flip with X2 the second qubit, and psi 3 you flip the third qubit. So you will then, at the end here, you will measure the ancillary qubits. And we'll get X or Y, each will be 0 or 1. There's 4 possibilities. And each of these 4 states will give us the different possibility for the measurement on the ancillary qubits, X and Y. So let's see. Supposing we take psi 1. So this first qubit was flipped. So this is a 1. It should. So okay, there's 2 bits. There's a 0, 0, 0 plus 1, 1, 1. Let's take the 0, 0, 0 bit, which is corrupted. So the bit 1 is flipped to 1. So what that does is that flips with the control X this first ancilla. The first ancilla is also connected to the second physical qubit, but that has not been flipped. So the first ancilla will be flipped once, and so you'll get 1. So that's what this is here, 1. The second ancilla, all right, so we're in the state, considering the state 0, 0, 1. The second ancilla is coupled to the physical bits 2 and 3, which are both 0, so that gives Y equals 0. And that's what we have here. So that was when we took the piece of the input wave function 0, 0, 0. What about the other piece, which would then be, so this is the one we're dealing with, 1, 1, 0. So remember, the right-hand one is bit 1. So that's a 0. So this does not flip the ancilla. But bit 2 is 1, so that does flip the ancilla. So again, we get X equals 1. So the whole point is, for both pieces of the wave function, we get the same value for these ancillary qubits. So in this case, we get X equals 1. And you can similarly convince yourself that if I take this piece, the 1, 1, 0, I still get Y equals 0. And you can go through the other possibilities. And for psi 2, psi 3, you get the other values for X and Y. So if you then measure X and Y, you can tell which of these 4 syndromes, these 4 states, the uncorrupted and the 3 possible corrupted ones, you have. So you do measurement. That's done here. The measurement is done on the ancillas, but then you can correct the physical qubits. So for example, if you find that X and Y were both 1, that's psi 2, so we have to correct with an X. We have to correct this qubit has to be flipped. So if X and Y are equal to 1, that's what this means. Big X to the power little x times Y, so that's 1. So this flips and the other 2 don't flip. The power of this one is X, Y tilde. So if X is 1 and Y equals 0, you flip. And this is X tilde Y. So if X is 0 and Y equals 1, you flip. So this is the basic idea of how you do quantum error correction. You measure the ancillas, and then you correct the physical qubits. Now, there's another way of thinking about this, which is going to be very helpful when we generalize to include other types of errors. So if you look at these 4 states, which are written here, it's instructive to consider the values of these operators, Z1, Z2, and Z2, Z3. And we'll see why these are useful in a minute. These are called stabilizers. Now, first of all, Z1, Z2 commutes with Z2, Z3. So they're mutually commuting, so they can have simultaneous eigenvalues. I mean, the eigenvalues can have the same eigenvectors. So if you consider psi naught, what is Z1, Z2? Well, so we're acting on these 2 qubits. Zeros don't flip. Here, both ones flip. So you get an eigenvalue of 1. These operators are eigenvalues of these states. That's important. And they mutually commute, so these states have simultaneous eigenvalues of these operators. And what are those eigenvalues? Well, either you can just figure it out, put the multiply by the operator, or a little more elegant. Oh, I should also point out that since these operators, when you square them, are 1, the eigenvalues are going to be +1 or -1. And the question is it +1 or is it -1? What are the eigenvalues? Well, we've already said over there that the corrupted state, psi I, where I equals 1, 2, and 3, are obtained by acting with the appropriate X operator, the flip operator, on the unperturbed state. So now we can figure out what the eigenvalue of, say, Z1, Z2 is, acting, say, on psi 2. That's Z1, Z2 times X2 acting on psi naught. And now we have to remember that on different bits, the Z's and the X's commute, but on the same bit, they anti-commute. So I have to bring the X to the left, which I want to do, I have to pull it through one of these variables which anti-commutes and the other which commutes. So this is minus X2 Z1, Z2 psi naught, and this is just psi 2. Sorry, X2 Z1, Z2 what am I trying to do here? Minus X2 okay, sorry. But this psi naught has eigenvalue 1. So this is the same as psi naught. And minus X2 psi naught is minus psi 2. So the eigenvalue is minus 1 corresponds to X2 anti-commutes with this stabilizer Z1, Z2. Whereas, for example, X3 commutes with Z1, Z2 because the X operator is distinct from all these. There's no anti-commutation. So for X3, just line them up a bit better. The eigenvalue is 1. Okay. I beg your pardon? So Xi commutes with Zj, that's the commutator symbol, if I is not equal to j. But if I is equal to j, then this curly brackets is the symbol for anti-commutator Xi, Zi, That's equal to 0. Okay, so Z1, Z2, Z2, Z3 are called stabilizers. And if you look at these eigenvalues, Z1 for Z1, Z2, they correspond to the X values here. You see that the eigenvalue of Z1, Z2 is -1 to the X. Just look at those 4 possibilities. And similarly, the eigenvalue of Z2, Z3 is -1 to the Y. So what we're going to do is rewrite our circuit in a way equivalent to this, but where we focus on measuring these stabilizers. And from the measurements of the stabilizers, we can deduce what error correction we have to do. So I guess I'm going to erase this and write it in an equivalent way. Which will display explicitly the stabilizer operators. Okay. So we're going to, as we'll see, I will explain this once I've drawn it. We're going to need Hadamard's, our old friends here. And we measure and we get X. And then for the second ancilla, we have a Hadamard, and we're also going to have a control H, and this will be Y. And then the first ancilla will be a control Z, will be the control bit for a control Z gate, which targets the first 2 of the physical qubits. So that's Z1, Z2. This is going to be our first stabilizer. So what this means is that if this control qubit is 1, the operator Z acts both on qubit 1 and qubit 2. And similarly for the second ancilla, that is a control Z. Yes, that's right. For qubits 2 and 3. So this second control Z gate, where there's 2 target qubits, corresponds to Z2, Z3. So this is the second stabilizer. And what I'm claiming is that this is completely equivalent to what we had before. I'll explain why in a minute, but it's a more intuitive way of looking at it because you display explicitly the stabilizers, which will be a much more convenient way of looking at this situation when we have more complicated error correction codes which correct for phase flips and so on. So why is this? Okay, let's see. So we're using these identities that we've discussed earlier in the course. Now, we've said that for control Z gates, I'm running out of space. Can I erase this? I guess I'm going to erase it. For control Z gates, there's an equivalence between the control qubit and the target qubit, or in this case, there's 2 target qubits. So that's equivalent to putting a Z we still have the H, but now the target qubit is the ancilla, and since it's coupled to 2 of the other qubits, we're going to need 2 of these. So this is using the fact you can invert the target and control qubits for control Z. We discussed that in an earlier lecture. And if I stick in here 2 Hadamards, which I can do because H squared is 1, and I use the fact that HZH, oops, that's the same as X. This becomes X and X. Which was the form of the circuit I wrote down originally, what was on the board when you came in. So we're going to be thinking about stabilizers. This is the most convenient way of doing it. And if you if you put in these Hadamards and then the Ancillas, then you just have to put the stabilizers in these double controlled, not controlled, in this case, control Z gates. But the same thing is true. You measure X and Y, and they determine then the eigenvalues of Z1 and Z2 and Z2, Z3. And you measure both of those, and then you know that the system is in an eigenstate. Say, in this case, Z1, Z2 is -1, Z2, Z3 is +1. If the only states around are these 4 syndromes, which I just had to erase, then you know that must be, you project onto state psi1. And then you can error correct that by flipping the appropriate thing. Okay. So let me just point out in general why this works. Because this, yeah. So let's supposing we have a state psi. And this state is an eigenstate of some operator, let's call it O in general. And the eigenvalues of O, we know, are plus or minus 1. This is going to be one of the stabilizers, and we're specifically going to choose them with eigenvalues plus or minus 1. And also, they have to all commute with each other, so they have simultaneous eigenvectors. Okay, so and we have an ancilla, which is initially in state 0, as we were discussing here, goes through a Hadamard, and then we're going to have a control. This is the control qubit, and then that has another H, and then we're going to measure it, and this is going to be a control O gate, which means the following. What it means is, as for the other control gates, if target qubit equals 0, do nothing. If target qubit equals 1, act with the operator O on the... Oh, no, sorry. Yeah. Sorry, yes. This is the control qubit, sorry. Thank you for keeping me in order here. Control qubit equals... If control qubit equals 1, act with O on the target qubit. So if the target qubit is in an eigenstate with eigenvalue 1, again, you do nothing. If the target qubit is in a state with eigenvalue of O equal to -1, then you act with O on it, which changes the sign. So what I'm going to claim then is that this measurement here will give you, well, it will give x equals 0 if the eigenvalue is 1, and it will give x equals 1 if the eigenvalue is -1. So in general, as I said over there, it's not a coincidence, the eigenvalue is -1 to the x. So let's see why that is. Okay, so let's, So what is the state of the ancillary qubit here? It's 1 over root 2, 0 plus 1. And let's suppose that the eigenvalue of O is -1. So then okay, let's suppose first of all it's +1. Now, so for the piece here corresponding to 0, this control gate does nothing. For the piece corresponding to 1, it acts on psi with O. But the eigenvalue is 1, so again it does nothing. So in that case, we'd get 0 plus 1. And that would give 0. So now I'm going to try and use a different color to indicate, supposing now the eigenvalue of O is -1. So the state here is still the same, Hadamard 0, 0 plus 1. Now, for the 0 piece, we do nothing. So coming out of here, it'd be 1 over root 2 times 0. But the bit of the linear combination correspond to 1, we add with O, which changes the sign, because the eigenvalue is minus 1. So it's minus 1. And then this state acting on with the Hadamard then gives you 1. So the eigenvalue of, oh, this is messed up here. Yes, here it is. Let me highlight that. So we measure x, and from that you can tell whether this state psi has eigenvalue plus 1 or minus 1 for the operator O. Without directly measuring it. You measure the ancilla, but this coupling gives you the information that you need. Okay. So that's the first part of the talk. We're going to, this will be essential. It's conceptual way of viewing things when we do more complicated error correcting codes which correct for phase flips as well. But before that, I have to say a word then about what sort of errors can we have. Okay. So we're going to change gear a little bit. Because these errors come because our qubit is coupled to the environment. So we're going to have to talk about the environment. So we might have a qubit X. But there's also the environment. So let me write the environment as a second state here, labeled by E. Now, ideally, if you had a perfect quantum computer, X will just evolve, this qubit will just evolve independent of the environment. Unfortunately, that's not the case. There's a coupling. And that will cause the qubit to become entangled, as we say, with the environment. So, for example, if we were in the qubit was 0, and similarly, I'm putting the environment state before. It doesn't matter, of course. So we run the quantum computer. With time, there's a bit of noise, and the sum of state 1 of the qubit might have crept in by coupling to the environment. So E0 and E1 are states of the environment. They're not necessarily normalized or orthogonal. And similarly, E on 1, we can write as an environment state E2 plus an environment state E3 times 1. Yes? Yes, the noise comes from the environment. Yes, the noise is the coupling between the environment and the qubit. So basically the same thing, yes. So if the error rate is small, then the amplitude of the environment states E1 and E2 will be very small. Will be very much less than 1, and E2, the normalization of that, so it's not very much less than 1. And state E0 will be not that different from the original environment state E, and similarly E3 here will be not that different from the original environment state as well, E. So we want these to combine these together in such a way that we can apply it for a general qubit state X, valid for both X equals 0 and 1. So I'm just going to write this out. It's just pretty obvious that something like this must be true, and you can check it yourself afterwards. Okay. So E0 plus E2 over 2 times the identity. All this is going to act on the state of the qubit, plus E0 minus 3 times the Z operator, plus E2 minus, plus E1. The main thing I'm interested in is not so much the details of the pluses and the minuses, but the structure of it. It's E2 minus E1, and this must be Y. Aha, Y is appearing. Somebody asked about Y in an earlier lecture. Here it will appear. And so identity X and Z are the familiar operators acting on the qubit, and Y is Z times X, which is 0, 1, minus 1, 0. The Pauli spin operator would have an extra factor I in there. It's not usually considered necessary to put that in doing the quantum computing. Well, I mean, all these E0 plus E2 over 2, that's just another state of the environment. So let's just give this a simpler label. It's just to say that this state of the environment and a qubit initially in X equals 0 or 1 will map into a linear combination of states. So first of all, where X is unchanged, and that we'll call that environment variable D. And then A, where X got flipped. These are just environment states plus B times Y plus C times Z. It's just saying that basically that if you start with some initial state, you can get other states by acting on with X and Y and Z, and that's all you can do since there's only two states. So this is true for, this is true for all X, so it's true for a linear superposition. So, state of the environment times a state of a qubit, single qubit psi, which is in a linear superposition of 0 and 1, will, in the presence of noise, get changed to this sum, where this first term, psi, is unchanged. The second term, with a different environment state, it will be acting with X, and this is what's called a bit flip error. and a different environment state times y plus a different environment state c times z, acting on the original qubit state psi. So x flips the bit, z, as we discussed, gives a phase error. The relative phase of the 0 and 1 piece is flipped. And y is a combined phase and bit flip error. So these are the errors we're going to have to correct. Bit flip error, we already discussed that, but we now need additionally to include phase error and a combination of bit flip and phase. We've got to correct all these. So what we're going to do then is write our one logical qubit in terms of several physical qubits in order to detect if any of those physical qubits got corrupted. So we're going to use an n-qubit, and we use the word code word for the set of qubits which represent one logical qubit. And I'm going to give an example due to Peter Shaw where n is 9. We extend the 1 qubit not to 3 but to 9 in order to deal with these different types of errors. This is not the most efficient, but I think it's the one that's easiest to see the structure. So we have a state of the environment, and we have a state of n qubits in our code word. So what errors can appear? Well, first of all, the first term, there's no error, the identity. And then each of the n qubits can be flipped with x for that qubit. And similarly, we can have a combined phase and bit flip on any of the n qubits, that's represented by y. And we can have pure phase flips represented by z on psi with n qubits. So we're going to, I should emphasize here, we're assuming that only one qubit gets corrupted. So the error rate is sufficiently low that this is a good approximation. So what is going to be involved then in this now general quantum error correction? So first of all, as we've said, we expand the logical qubit, 0 or 1, to an n bit to an n qubit code word. Then, by using a set of stabilizers, we're going to project the state which is possibly corrupted So on one of the possibly corrupted states in this expression, there are 3n plus 1 of them, 1 being the uncorrupted state, and then there's 3n possibly corrupted states. By determining the eigenvalues of a set of stabilizers. And these eigenvalues of the stabilizers, +1 or -1, will uniquely determine which of these 3n+1 states are projected onto. And we'll see an example of that in a little while. And then finally, if you project onto a corrupted state, you correct, if necessary, by acting with the appropriate operator So for example, if the eigenvalues of your stabilizers tell you that you project onto the state where the ith bit had flipped, you act on it with xi. Or if you find that there was a phase flip on the ith qubit, that's one of these, you project onto one of these, then you would act on it with zi. Or if it's both phase and flip, yi. All right. Now it may look as though doing phase errors is harder than doing bit flips. Bit flips, we could sort of see pretty clearly what was going on. However, yeah. I beg your pardon? Earlier, I had, am I getting, is this wrong? N equals, I had n equals 3, but I don't get this 3 because I'd ignored the y's and the z's. So I had n plus 1 with n equals 3, and there was 4 when there were 4 states. And I could determine, and with 2 stabilizers, I have 2 squared possible sets of eigenvalues, so I can distinguish between 4 states. So we'll need similar considerations here. So before we do the full thing, where we correct all these errors, let's just do another simple case, and that is the phase flip. Phase errors. Another. So the error we're talking about is where alpha 0 plus beta 1 goes to alpha 0 minus beta 1. So the point I'm now going to make is that if instead of using the z basis, which is what we've been doing, we go to the x basis, then in the x basis, this is just like flipping the bit. So we're going to in the x basis, you remember we discussed these are what you get by the Hadamards, plus equals 1 over root 2, 0 plus 1, and minus is 1 over root 2, 0 minus 1. So what we're calling a phase flip in the z basis actually corresponds to a bit flip in the x basis. How do we transform from z basis to x basis? We use these Hadamards. Okay. So you're saying I have a phase of pi here. Okay. So what we're going to do, we will be able, in the final version, which we haven't got to yet, to be able to correct arbitrary phase errors. Supposing there's just a small phase error crept in. So you remember, by measuring these syndromes, we're going to by measuring these stabilizers, we're going to project onto one of these states. One of the states will be the uncorrupted state. Another state will be where this flip, where there was a phase error of pi on this flip. Now, suppose the state that you feed in has just a small phase error. With high probability, you will project onto the uncorrupted state and do nothing. But there is some small probability that you will project onto the state with phase flip pi, and then you will correct for the phase flip pi. So this is going to be how we will be able to correct for arbitrary errors by projecting onto one of these 3n plus 1 states. It's pretty smart, actually. Okay, well, so how are we going to do it? So, encoding. So the 0 state will not be encoded by 0, 0, 0, but by plus, plus, plus. And the 1 state by minus, minus, minus. So remember that a Hadamard acting on 0 gives a plus, and a Hadamard acting on a 1 gives you minus. So how can we create this initial encoding? Okay, so we start with a state psi, which can be a linear combination of 0 and 1. And we need 2 other qubits. And we're going to do the following, and then we'll check that it works. Because the Hadamards are going to come in. Okay, so supposing, so this is a linear combination of alpha 0 and beta 1. Let's consider the 0 bit. So if this is 0, then it does nothing. It does not flip the second bit. It does not flip this third bit. So here we have 0, 0, 0. And that comes out as plus, plus, plus out of the Hadamards. Now supposing we consider the piece of involving basis state 1, then that does flip these two other qubits. So before we go into the Hadamards, we have 1, 1, 1. And then the Hadamards convert 1 to minus. So this is how we create our initial state. So the stabilizers, then, since in the X basis, the phase flip looks like a bit flip, will be the analog of Z1, Z2, and Z2, Z3, but we've got to convert to the X basis. So we have to put in Hadamards, and I write times 3, because there's 3 qubits. This will be say the first of those stabilizers. This other one will be just the same. So you recall that h squared is 1. So I've inserted an extra couple of Hadamards here because h squared is 1. And these h squared here also equal to 1. And h is just x, as you will recall. So if you just want to detect phase flips, the stabilizers would be x1, x2, and x2, x3. Okay. All right, so now, with those preliminaries, we've got to put everything together and try to correct for all those 3 types of error: bit flip, phase error, and combined bit flip and phase. And there are been a number of codes proposed. Some of the early codes were proposed by Peter Shaw again, and the different one by Andrew Steen. It turns out the smallest number, the smallest size of code word that you can get away with is n equals 5. And there's a specific form for that, which you can read about in the books. It turns out, in terms of the hardware, it's somewhat difficult to implement. A popular choice is that due to Steen, which is for n equals 7. So each logical qubit is expanded to 7 physical qubits. And in his original work, Peter Shaw had a one where the code word is expanded to 9 qubits. So this Shaw scheme is mainly now of historical interest because it's not most efficient. There's quite a bit of redundancy in it. And so you wouldn't actually use this if you were trying to really build an actual quantum computer with error correction. But to me, I think this is the easiest intuitively, because it sort of combines in a natural way the bit flip errors and the phase errors. So I'm going to discuss this. Okay. Now, so you first encode for phase flips. So 0 goes to plus, 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 and 1 goes to minus, minus, minus. And then encode for bit flips. So plus, which is 1 over root 2, 0 plus 1. This will just get triplicated as before. 1 over root 2, 0, 0, 0, plus 1, 1, 1. And this triplication is done for each of the 3 here in the plus, plus, plus. So we get 9 altogether. And so the plus, so the 0 goes to 1 over 2 root 2, because we have 3 times this 1 over root 2. Zero, 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 plus 1, 1, 1. And then there's 3 sets of qubits like this. And 1 goes to 1 over root 2, 2 root 2, 0, 0, 0, minus 1, 1, 1, and that's also triplicated. Okay. So let's see how we might encode some initial state in this way. Okay. So I will draw the diagram and then explain it. So we're going to feed in some state psi here, and we're going to consider the 2 possibilities of 0 and 1. Of course, we're going to have Hadamards, and we're going to have control gates. That's going to be our first 3, and then we're going to go down, and there's a 0 here of our control. It's equivalent to a control X gate. And then this is going to go as before through a Hadamard. Then this is just going to repeat 3 times this right-hand bit of the diagram. And then there's the third one. We have to end up with 9 qubits. These boards are not quite tall enough for these diagrams. So I'm just triplicating the right-hand part. So let's assume then, so psi in general will be alpha 0 plus beta 1. Supposing we put 0 in there. So this state is 0. And these that because this is a control qubit, nothing is changed on these target qubits. So these are all 0. And then they go into a Hadamard, and you get 1 over root 2, 0 plus 1. So if you consider the bit 0, then these control knots don't do anything to these gates, and we get 0, 0, 0. But if we consider the 1 part, then the target bits get flipped, so it's plus 1, 1, 1, and 1 over root 2. So what I'm drawing here in orange is what you would get if you fed in 0. And then everything is just repeated down here. And you can check yourself that if I fed in a 1 in blue, then I would get out here 1 over root 2, 0, 0, 0, minus 1, 1, 1. I'll leave you to do that. And again, this is just repeated for each of the blocks of 3. So this is how you encode it. Now, how do you do the error correction? So I'm going to show this on the screen. Oh. Okay, so this is naturally a bit more complicated, and we're not going to go through everything in detail, but I want to illustrate at least a bit of how it works. So the top part just shows the encoding, which is what I wrote down here, and you can check afterwards. The lower part then is how you do the error correction. So there are 8 stabilizers. They correspond to the top 8 lines, each of which starts with a Hadamard. The lower 9 lines, they're the actual physical qubits among which we want to check for an error. So the stabilizers you can read it off from these as 1, 2, 3, 4, 5, 6, 7, 8 stabilizers. This one has 6 X's, 6 X's, 2 Z's, 2 Z's, 2 Z's, and so on. And I'm not going to go through all the possibilities, but give you some idea how it is that each of these stabilizers, which has an eigenvalue of plus or minus 1, when I know all 8 eigenvalues, whether it's plus or minus 1, I know which of the possible corrupted states is feeding in on the left-hand side. Of course, you can tell it's redundant because 2 to the 8 possibilities of plus or minus 1 eigenvalues is what, 256? But there's only 9 times 3 plus 1, 28 states. So there's clearly a lot of redundancy, and there are others which are more efficient, but this has a structure to it which I think is appealing. Okay, how are we doing here? Okay. So the stabilizers, which you can read off from the diagram, are so you want the 6 pairs of Z's. Did I get this right? 1, 1, 2, 2, 3, 4, 5, 5, 6, 7, 8, 8, 9. And then we have to do something for phase flip, so there's 2 rather complicated stabilizers involving x's, in fact a product of 6 x's. This first one is a product of x's for the first 2 groups of 3. The second one is a product of x's for the second 2 groups of 3. Now, so let's see. We'll maybe just do a couple of examples. Okay. So supposing then there is a phase flip on the first qubit, Z1. So remember, to get the eigenvalues of the stabilizers, we have to see whether the operator which causes the error, in this case Z1, commutes or anti-commutes with these stabilizers. So you see that it commutes with all 6 of the Z's, and it anti-commutes with the 2 X stabilizers. Sorry, I got that. I said that wrong. Sorry. Z1 anti-commutes with the first stabilizer, but commutes with the second one because there's no X1. So that's how you can distinguish it from the other phase errors. Supposing we have a bit flip error, X1. So the eigenvalue then, so this anti-commutes with Z1, Z2, so the eigenvalue of this one will be -1. These will all be +1. And the eigenvalues are, so X1 commutes with both these stabilizers involving X, so these will be both +1, that was not the case for the phase flip, and one of these will be -1. And which of these is -1 can tell you which of the ones had a bit flip. And if you have a bit and phase error, say on the first qubit, so that's caused by Y1, so the commutation with the Z stabilizers, that will be the same as if it was an X error. But you can tell then it's not an X error, it's a Y error, because the Y1 anti-commutes with X1, so the eigenvalue of this stabilizer will be -1. And so there's a lot of possibilities. I'm certainly not going to go through them, but I hope you get the idea that you can distinguish which of these 28 9 times 3 plus 1 states you have projected onto. Once you've projected onto it, then you can error correct by acting with the appropriate quantity. So I emphasize then that by correcting for this discrete set of errors, 27, you actually, or by projecting onto these 27 states, you correct for some arbitrary error, because the state of the qubit depends on continuous parameters, But what you're doing is you're projecting on whatever the initial state is, you're projecting onto one of these syndromes and then able to correct it. Okay. So I want to say in a couple of minutes and then stop about what's called fault-tolerant quantum computing. You see, we really haven't done enough yet. We've got to start. We've seen how we can do quantum error correction, which was originally thought to be impossible. So we're correcting sort of stored information or transmitted information. But how are we doing that? Well, we have some pretty complicated circuit with lots of gates. And what are these gates going to do? They're going to add errors. So we have to be careful that the error correction doesn't add more errors than it's trying to solve. So there's an important result in quantum computing which says that if the hardware components fail or give an error with some probability p, which is less than a threshold, this is called the threshold theorem. So if p is, the error rate is less than some threshold, then you can use error correction to reduce the error to some value less than p. Now, this gets pretty technical. From what I read, for this quite favored 7-bit Steen code that I didn't describe in detail, the error rate is something like, the threshold is something like 10 to the minus 4 or 10 to the minus 5. This is pretty stringent. I don't think one can do that at the moment. But if you can have an intrinsic error rate less than the threshold, then you can do error correction to reduce the error rate below that. And then you can concatenate this idea multiple times. So for the first time, each qubit is represented by, I don't know, 7 or whatever other qubits, and we've succeeded in reducing the error by a bit. But then each of those, you can do it again, and each of those can be represented by 7. And you can successively concatenate this error correction. The price is you have an enormous number of qubits, but you can, at least in principle, successively reduce the error rate down and down and down, the price of a very large number of qubits, to hopefully some acceptable level. So how many might you expect to need qubits if you're doing this fault-tolerant quantum computation, you're doing error correction? And there's a paper by John Martinez et al. In Phys. Rev. A 8620322324, and that's in 2012, so it's not very recent. So John Martinez has very good superconducting qubits, and this is a very highly technical paper on a different way of doing error correction, something called surface codes, which I don't really understand, for which the threshold is more like 1%, 0.01, rather than 10 to the minus 4. So Martinez reckons he can produce his superconducting qubits with an error rate less than that. Okay, so supposing then we wanted to do Shor's algorithm to factor an integer which is too big to be factored by a classical computer, so something like 6,000 digits or 2,000 bits. Using these superconducting qubits and concatenating multiple times this error correction to get the error rate down to something which is acceptable. And the number that's in the paper is about 220 million. which is a huge number. This is the number of qubits that you would need to do Shor algorithm with error correction using these surface codes with currently available superconducting qubits. So, I mean, for the size of quantum computers that have been used so far in the gate model, at least, maybe it's 5, maybe it's 10. I think Google and Microsoft are trying to do 50, but there's still a long way to go. Now, that's not to say it's impossible. If you think of the incredible integration of superconducting circuits, perhaps in some distant future, this might be feasible. Perhaps also the intrinsic error rate on the individual qubits might be much lower, and then you wouldn't have to concatenate so many times to get the error rate down to something acceptable. But anyway, this is what I'd like to end with my conclusion then, that the gate model of quantum computing is a fantastic subject, but I think we're still far away from having a quantum computer which would solve problems that a classical computer could not solve. Okay. Oh, timing worked out about right. I wasn't sure whether it would do. Okay. Any questions? There's this large number because of the error correction. You mean you just need maybe a few thousand logical qubits to do the Shor's algorithm, but you need many, many times that to get the error rate, to do the error correction enough times to get the error rate low enough.
But this is for how many qubits the computation is there? Because
so this is to factor a 2,000-bit integer.
Okay.
And my understanding is that's about what cannot be done classically.
Okay. And what is the order of redundancy that we have in our usual classical computers these days? Like, I mean, just the order.
Well, in classical computers, you don't need error correction.
You don't need, because of thermal.
It's my understanding that the devices in which the bits are stored are sufficiently big compared with an atomic scale that you don't need it. Also, there's a big jump from 0 to 1. There's nothing in between with anything sort of low energy. So it's a huge fluctuation to go from 0 to 1. So you don't need error correction in classical computers. The chips are just sufficiently accurate without needing it. But that's definitely not the case for a quantum computer.
Thank you.
No, it's okay, you first, and then you.
There is something called topological quantum
Yeah, right.
where you don't have to bother about the data because things are only for.
So topological quantum computers, that's right. So this is where the individual qubits are stored in a complicated many-body state of some system, and 0 and 1 will be different many-body states with different topological quantum numbers. So to go from a 0 to a 1, you've got to make a topological change. In other words, a big change. You can't just locally make a change. So the idea there is you bring down the intrinsic error rate, not to 0, but low. So that is the real motivation for topological computing, is to be on the right side of this threshold theorem. But the systems that have been proposed are very esoteric, and I'm not sure that any sort of quantum computing device yet has been demonstrated with topological quantum computers. But there is definitely quite a bit of interest, and I know that Microsoft has an effort at Santa Barbara which is working on this. So the goal then is to reach, the idea is that with those, you will have a much lower intrinsic error rate, so then you could do the error correction. You had a question.
It's a vague question, but can you use other kinds of quantum systems as not qubits, but I don't know,
You mean 3-state systems?
and states, does that help in any way?
I don't think it helps. People call that qubits. So if you had not 2 states, but 3 states or 4 states, people talk about that. I'm not aware that people seriously think that they would be superior for doing quantum computation than a computer based on qubits.
Okay, so if there are no other questions, let's thank Peter for a wonderful set of lectures.